Hello, everybody. Thanks for taking some time to listen into this session from the OCP Virtual Summit. I am Eric Rydell from IT Renew. I'm the Senior Vice President of Engineering for the Sesame product division. And I'm going to talk to you today about some technology case study that we've done from servers to serverless in 10 minutes. So first, let me briefly introduce IT Renew and Sesame. What we're doing is building a product line of rack scale appliances, storage, compute, and networking integrated into servers that customers can roll into their data centers and use for some of their most demanding workloads. The point of this technology is to bring hyperscale, the advances in hyperscale over the last 10, 15 years to a wider audience, so that customers can take advantage of the scalable designs, the power efficiency, the design efficiency, design simplicity of open architectures, and use it for their own workloads. And finally, within IT Renew, because of the way that we source and build these racks, we're able to offer best-in-class TCO, sort of never seen before levels of TCO. And I'm not going to talk about that in detail in this slide, but feel free to catch up with us after or separately. So what I do want to talk about today is how we go from servers, as shown here, so racks of servers in your data centers, or racks of servers as they are delivered in trucks to your data center, to serverless. And serverless is really the software. It's one of the paradigms used in cloud native software today. So it represents the software that runs customer workloads. So we're trying to bridge the gap from hardware servers that roll off a truck to the software that runs your customer workload. And we're trying to reduce the amount of time that it takes from when the hardware rolls into the data center, you plug it into the wall, plug it into your network, and begin running workload. So we're trying to minimize the time between when the servers are powered up to when you can run customer workload. So we're going to see if we can do this in under 10 minutes for a rack worth of equipment. The project goals here were to have pre-designed and pre-qualified solutions for several key computing use cases. So we're trying to improve OCP adoption for a wider set of customers and enterprises by simplifying the ability to roll in these solutions. What we're doing at Sesame is simplifying the hardware aspect of this, the design integration of racks themselves. But what the point of this talk is that a slightly further amount of integration is also useful with the various infrastructure stacks and software partners that we're working with in order to, again, pre-qualify and pre-design that those software stacks will work smoothly and efficiently when they're rolled into a customer's data center. So the first view here, this is a visual of one of our Sesame racks from IT Renew. We have 45 dual socket OCP Leopard servers in a rack. We have top of rack switches. We have some ingress egress nodes, as is standard in some of the use cases, and actually 2 layers of switches. This is a logical diagram of that same rack layout. So we have 2 power zones, a total of 45 nodes, and we have nodes of 3 different types. We have the nodes shown in red are dual socket compute nodes. The nodes shown in blue are storage nodes with 1 terabyte, 8 terabyte, or 15 terabytes of NVMe storage on board. And finally, the green nodes are manageability and infrastructure nodes used for common services in infrastructure, for example, DHCP, DNS, which we'll talk about some more. In the management layer, etcd, dashboards, monitoring software. And at the top of the rack, ingress egress nodes. This is a common modality in, for example, in Kubernetes environments, where in order to provide virtualized networks, there's a set of nodes that process all the packets. And so the point of the green nodes is just to be able to host these infrastructure services with a modest kind of compute and storage footprint. So we have three types of nodes integrated into a rack. And as I said, what we ship as a Sesame for Open Systems solution is a fully integrated qualified rack with all of the cabling, storage devices, networking devices, all the compute, firmware, everything is tested and integrated as a whole and pre-qualified with selected software stacks, as we'll talk about in the rest of the discussion. So as a reminder, again, the nodes themselves are from the OCP Open Designs. It's an OCP 2-socket Leopard node, simplified design, highly scalable. These are nodes that are running today and over the last several years at the level of thousands, hundreds of thousands, sometimes millions of nodes in fleets of hyperscale data centers across the world. And the same technology is being made accessible by Sesame. So in addition to the rack level solution on the right-hand side, on the left-hand side, we're also showing our Discovery Fast Start appliance. This is a design that we've created at IT Renew that hosts up to 5 of these same compute nodes, the exact same nodes that we use in the rack, and in a desk-side enclosure. So this enclosure is able to fit under your desk or in a corner of your lab, plugs into 110, 220 standard power outlet, and has up to 5 compute nodes. The configuration that we're using here is 4 compute nodes and an infrastructure node. We have an ATX gaming power supply in the bottom of the enclosure at 1600 watts. So that's the maximum power draw of these nodes, but still allows a very powerful set of computing, as we'll indicate. This is the visual of that same node plugging in the power at your desk, plug in a symbol RJ45 uplink, and the compute nodes shut the door, and everything is running and ready to go. And this is the demo unit that we'll use for the case study today. So now let's talk about the software infrastructure layers. It's really the point of the talk. What we've done, the prerequisites for starting this deployment comes in 3 layers of infrastructure software. There are several choices that can be made in each of these layers. What we're showing here is the choices that we've made and then the practical services that are deployed as a result. So we have a Linux operating system layer. In our case, we choose Ubuntu. We have a DevOps layer. In this case, Docker and Ansible. Again, there are other tools, other frameworks that might be used, but we do need the adaptability of a DevOps deployment type of tooling. And finally, an automation or orchestration layer. In this case, we're using Rancher from Rancher Labs, which is a Kubernetes-based distribution. So as a result, the practical deployed services from each of these layers, we use DRP, so Pixie server, and a DHCP from the Linux base. We use something called Digital Rebar and the Docker registry from the Docker Ansible suite. And finally, Rancher RKE, the Kubernetes environment in Rancher for the automation and orchestration. So the reason we call this prerequisites is that customers and companies will choose which tools they want to use at each of these layers. Again, there are several vendors and several options. These are the ones that we've chosen, but this is something that has to be done before you start deploying the software. And so let's take a look at what we have to do next. So the first step is to Pixie boot the entire rack. So what we do is we use the IPMI APIs to attach to the BMC, the baseboard management controller on each node. For those that aren't familiar, this is a small embedded CPU that manages the large CPUs, the 2-socket Intel CPUs in the node. So this allows us to power on the node, power off the node, and do low-level manageability commands. So we use the IPMI toolset to power on each node, and then Pixie is used to serve an operating system image, which is installed on an onboard mSATA device that we have on each of the nodes. And finally, the node is rebooted from scratch. What we show is the time it takes for each of these steps. So you'll see that some of this time already breaks our 10-minute kind of target budget. But the good news is that there are a couple of areas, two of which are listed in the parenthetical. So there's 2 minutes of timeout in the Pixie process, and there's a 30-second timeout on the Grub, the boot menu, that are captured also in these timings. Those are absolute idle times. And in addition, there's a number of sub processes within the 3 processes shown where we believe we can further reduce the time. So there is some amount of time in these 3 steps, but we think it can be gotten to something on the order of 6 or 7 minutes, perhaps. So that's the first step. Just a quick reminder: we're booting 4 compute nodes here. Each of the nodes is a dual socket 12-core CPU, 256 gigabytes of memory. We have 10 gigabit Ethernet within the fast start unit. Our racks run with 25 gig as the standard. So this unit right here under your desk is 96 cores and 1 terabyte of memory. So as I said, a very powerful computing platform. And we built this for customers to do software benchmarking, POCs, exactly the types of case studies and demonstrations as I'm going through here. But it's much more accessible than if they have to bring an entire rack into the data center. So this is a solution that can be ordered, delivered in a couple of days and deployed in minutes, as I've outlined. So what we now see, we look into the manageability interface here. We're using a technology called RackN. We see that the 4 nodes in the system have successfully installed and booted. So we've completed the first step, served the Pixie image and done the install. So each of these nodes is now a full-fledged Linux node ready to run Linux workload. So the next step, we use Ansible to deploy Rancher. And in fact, we first deploy a provisioning server with Ansible, and then that provisioning server again uses Ansible, a little recursive, if you will, to deploy the RKE, Rancher Kubernetes environment, onto all of the nodes. So that's our next step. This provisioning server then deploys all of the Rancher tools and a set of background kind of libraries and other prerequisite packages into that deployed Kubernetes cluster. A small note here, since we're only using a 4-node cluster here, we have 1 controller, etcd, and 3 worker nodes. When we do this with an entire rack, 45 nodes, we would have at least 3 controller nodes, and the rest would be worker nodes. That's a use for those green infrastructure nodes that I showed in the logical Sesame diagrams. So our next step here, success of the Rancher deployment. So what we see here is the Rancher dashboard with 4 deployed nodes. You see that 3 of them have the worker role, as on the previous slide, and 1 of them is available for both infrastructure services and worker services. So we've got 4 nodes deployed. We see the 48 virtual cores from each of the machines. So there's dual 12-socket, dual 12-core CPUs. So it's 24 physical CPUs, 48 vCPUs once it's shown to the virtualization layer. And we see the RAM. There's a small discount has been taken on the RAM, 252 gigabytes, not 256. Right? And we show a number of pods running. I'll get back to that briefly again at the end. So here we show 9 out of 110 potential pods deployed at the Kubernetes level. The next step, step 3 in this process, is to configure the storage on these nodes. So remember, I told you there were also blue nodes in our rack that have NVMe, high performance NVMe storage devices on them. Configuring the storage is a little bit more of a complicated process since that's your permanent data. So we're not I'm not providing all the details in this talk for purposes of exposition. And we do have a blog post that you can look at that will give the full detail of both what we did explicitly in the storage configuration, as well as the rest of the story around this case study. But I'll save you the discussion in the talk. And finally, the fourth step, so once the storage is configured and the baseline nodes are configured, is to configure and provision workloads. In this case, we're using Ansible again, and Ansible is using Rancher to provision the pods within the cluster, as well as provision a set of monitoring tools. So the result is that we now have a Kubernetes level dashboard that allows us to see the cluster and node health, as well as various graphs of load and resource utilization provided by the monitoring tools that have been deployed. So here is the success of that fourth step. We see the dashboard within Rancher, and you see again percentage utilization for CPUs against that 192 virtual CPUs, utilization of the memory against that terabyte of collective memory on the 4 nodes, and the fraction of pods used against the configured maximum, right? And at the bottom of this dashboard, again, I won't go into here, those are familiar with Kubernetes, Grafana, and the various component metrics will be familiar. There are additional graphs and charts and plots for when these nodes are running workloads to diagnose issues or understand how hard the cluster is working, right? It's relatively standard dashboards. And so remember, I told you that one of our goals here was, can we do all this in 10 minutes? The bad news is that we don't quite achieve 10 minutes in this demonstration. I'm going through a video replay here of the various steps as seen from the Ansible level. We see that there is effort to do physical activities, powering on the nodes, waiting for the nodes to reboot. You see allusions to various waiting and timeouts, as I've mentioned on previous slides. We're doing at least 2 rounds of updating the software. Right, this is a favorite of software engineers and release engineers everywhere. Is kind of as soon as you roll some hardware in, you want to use the latest software, and the latest software was probably created 24 or 48 hours ago, and not a week ago when the system was shipped, or 3 weeks ago when the system was integrated. So there's a number of steps of upgrading to the latest software, connecting to the internet, and so on. Obviously, some of those processes can be short-circuited, and so we're still working to optimize those. You'll also notice in this display, there's a couple of underlying technology layers that are being used. So you see references to Kubernetes, which I've already mentioned. You see mention of Helm, recipes through Helm. See references to certificate managers. So there's also security certificates, RSA keys are being exchanged, security certificates are being verified. So there's quite a breadth of software functionality that is being taken care of behind the scenes of these various layers. Takes a little bit of time, but is also subject to optimization, right? And then finally, RKE brings up the ingress controllers, which I've already mentioned, right, at the top of the rack, process all of the nodes. And then finally, because we're interested in the timing here, it summarizes the total time that was taken by these processes, sorted in reverse order of what took the longest. And so, unfortunately, the total here adds up to something just beyond 30 minutes, so not quite the 10 minutes that we intended. But there is a number of stages that are quite amenable to further optimization and related to waiting for the hardware and so on. As you see, power up is 2 of the top 3 most timely pieces. So to summarize, kind of this point in the case study. So what we've done here is we've shown deployment in this 4-node cluster. This is exactly the type of POC that was done by one of our customers in the media and entertainment space. So they got one of our Discovery Fast Start appliances. They tried initial prototyping of deployment of their workload, and then they purchased from us a fully loaded rack with 27 workload nodes that they're using for their production platform. So the set of activities that I just discussed, different customers might make different choices of exactly which orchestration, which DevOps platform, even which Linux distribution they want to use. But this shows that the end-to-end success is quite achievable and recognizable in practice, as we've done with this particular Sesame customer noted in the slide here. I've mentioned several times that there are different stacks that can be used here. We did testing across multiple stacks, not just Rancher. So in the Rancher scenario, we were able to achieve in the best instance 20 minutes from from hardware start to cluster readiness. And Ksphere and Talos were a little bit longer in terms of deployment of the software stacks, but still well within that range of 10 minutes to less than an hour. We think we're well within the range, and we understand a lot of the tricks that we would have to pull to get under 10 minutes. Right? But we're quite confident that we've gotten ourselves in the ballpark. This isn't something that takes hours or days, certainly not weeks. This is something that is minutes to small digit hours, regardless of which stack you choose. Okay? Two other points of note on this slide I didn't talk about a lot. I mentioned briefly. What we've also done with all three of these platforms is a level of benchmarking for how many pods a particular node is able to host. What we actually tested was two different container types. So we have a sleep container, which literally does nothing except sleep. So it starts up the container and then the container goes to sleep. And so it's really testing kind of the null container, how much of zero workload containers can be hosted on the nodes. And you see that Rancher is able to achieve only 1,650 pods, containers on a single host, whereas Ksphere and Talos are able to do significantly more. But it's not that interesting since these are containers that do nothing. There is some variability here in terms of the technology that's being used, but at the end of the day, they're containers that do nothing. So our next step was the final row in the table, which is an Nginx container. So this is a small web server workload. And what you see here is that really each of the three platforms maxed out at 500 pods per node. There's a bit of detail underneath the asterisks in each case. Technically, Rancher didn't start to have problems until 507 pods. Ksphere did a bit better in that it didn't kind of completely crash until 550, and Talos pretty much maxed out at 500. Right. So we're comfortable that at the Kubernetes level of technology, each of the platforms are equivalently capable. Right. Might take them a little bit longer to get started, but once you're deploying a workload, they're all equivalently capable. And 500 pods, 500 containers on a single node is really pushing the envelope anyway, which is noted in the final kind of double star note at the bottom of my slide. The configured default maximum for Kubernetes is 110 containers on a pod. So we really push the envelope of performance testing by relaxing that limit. So each of these technologies is well able to achieve the 110 kind of design maximum. And for almost all workloads, that should be perfectly sufficient. So the good news is we've got three different choices for these technology stacks, a little bit of variability in how they're deployed, but the performance normalizes that, and you're able to achieve what the hardware is capable of. So In conclusion, kind of winding down the talk and the case study, we didn't quite achieve 10 minutes, but we know that 20 minutes is achievable in a 4-node cluster. And it is relatively clear to us, if you remember that summary table of where the time goes, that the gaps to 10 minutes are quite clear. In addition, when we perform the same testing on a 45-node cluster, we see some of the exact same kind of barriers and wait times. So we're quite confident that with a bit more engineering, a bit more cooperation with our software partners, we'll be able to get this into that less than a half an hour range. Perhaps even to the aspirational 10 minutes in practice with a little bit of teamwork and collaboration. I just want to briefly remind everyone, kind of the 2 products that we talked about is the Sesame Discovery Fast Start Appliance, desk side unit, OCP node capable, 4 or 5 nodes under your desk with 110, 220 power. And Sesame for Open Systems, which is a rack level solution up to 45 dual socket nodes in a rack, fully integrated, pre-configured from IT Renew. And they're available today in the OCP marketplace or at IT Renew's website. So call to action, come check us out in the OCP marketplace. If you have questions or comments on the talk or on the technology, feel free to reach out to me. This is me on Twitter, Rydell at work, or the QR code here leads to the Sesame Engineering GitHub. We're operating fully in the open compute hardware designs, open source software designs. So we're happy to share all the details of what we've accomplished. So if anyone has any questions, feel free to let me know now and I'll try to address them. Thank you. All right, thanks for listening in, everybody. I'm just going to answer a couple of the questions that came up during the session. Roberto, your question first. How are the storage nodes connected to the compute nodes? How do we manage the volumes for Kubernetes? So let me answer that first. So we actually tested 2 storage solutions. So OpenEBS. We ran on the nodes. We have 4 NVMe devices on the nodes in that Discovery chassis. In our rack level solutions, we also have JBOD solutions with HDDs. But we have NVMe in that one. So we used OpenEBS. We also experimented with Rancher's Longhorn. That's still in beta, but it fits with the rest of the Rancher environment. So that's how we're managing, kind of presenting the storage to Kubernetes. Our setup was not multi-tenant, but certainly there's no restriction on that. And then to Lesia's question about shifting from the POC to the larger rack. So that was very transparent for us. It was exactly the same technology. So we used the same Pixie Boot, DHCP, all those services that we discussed were hosted in one of the servers in the Discovery and the Fast Start unit, and they were hosted in one of the nodes in the rack. And so it's exactly the same experience. So we really just translated that directly over. And the only difference is that there's 40 nodes in the rack instead of 4 nodes in the Discovery. And then there was some commentary also about the speed of the setup. Yeah, so we're in general terms we're also pretty happy. Yeah, it would take you longer to remove the cardboard, especially if you're going to fold it up into a nice stack for recycling. It'll take you longer to stack up your cardboard than to get the software running. So we really see this as a successful kind of end result between the software infrastructure is very well designed for what we're trying to do, and then the hardware fits in. So we're just really matching up 2 technologies that taste great together, as it were. I think that covers all the questions. Ali's touched on a number of the other ones. We will update that blog link. So our apologies. That was a publication error. So we'll update the content of that blog in the next couple of hours, and folks can read more. So thanks for taking the time in virtual OCP, and enjoy the rest of your summit. Thanks, everybody.